actually joint work, and so the connection to physics is pretty loose. I think I would just say that as a main, let's say, of we'll try to understand a complicated problem that involves like training neural networks that have lots of parameters, and we're going to use this generic principle that maybe if you have a lot of parameters, a lot of things going on, perhaps you can gain some understanding by basically using mechanics, right? This idea of maybe understanding how things work in a some sort of average sense. So the setup here is going to be the standard supervised learning setup. Okay, perfect. Sorry. Now it's better, I hope. Okay. So it's a standard supervised learning setup where we are just considering, data points, xi, some labels, yi, and then a complicated model that has a lot of parameters, this theta, and just the thing that we have just a measure, a way to evaluate how good is a model. And so as you might know, like many of these modern deep learning techniques, they try to find good models by just using a single equation that essentially moves in parameter space by following some kind of estimator of the gradient, right? And so this estimator of the gradient can be like stochastic gradient. And so this equation, I mean, it's kind of has many puzzles, many things that still like very hard to actually get a grasp on, especially because they mixed different complicated questions, right? So there's a mix between optimization, so what kind of model should I use to approximate my functions in high-dimensional space? What are the properties, as we described, as we saw already from Florent, Lenka, and Giulio, of what are the behavior of like gradient descent methods to find good point in parameter space? And most importantly, what is the role, what is the effect of noise in the estimation of these gradients, right? And so this question is hard, but also very popular. So there's, of course, many prior work that try to attack different angles of this question. And so just to give you like some kind of snapshots of different areas in which angles in which you can attack it. So one can first try to develop some notion of some kind of an approximation theory that works on high dimensional spaces, right? So this is a kind of what we call a classic universal approximation results that that were very popular in the 90s and the early of the 80s, mostly done by works people like Andrew Barron, Peter Bartlett, Zivenko, and company. And these are results that, in a sense, are not satisfactory if you want to understand the whole picture, because they don't tell us how to find these good parameters, right? They're completely not learning agnostic. Then in the recent a wave of trying to understand deep networks, there has been interesting recent progress. In particular, trying to understand like the optimization landscape. We saw a talk about this with Giulio and also a little bit of Florent and Lenka. That kind of, in a sense, covers like both positive and negative results. And then also like recently, we have also, probably you have heard this word like many times by reading archive papers. There's this notion of overparameterized neural networks are good, right? And there's in the sense they are good, in the sense that we can prove statements about the global optimality of gradient descent in this regime. Okay, and we also saw yesterday Nati discussing how this overparameterization can relate, it can help us understand generalization. But in that picture, so what I will try to explain here in this talk is that maybe there's there's still like some important mysteries already in the simplest possible neural network you can imagine. That is the neural network that has a single hidden layer. Okay, and so in that case, we'll try to get some understanding. I'm hoping trying to present you some of the kind of outstanding problem questions that as I understand them, that essentially construct function approximations, right? Like your model is going to be a very kind of a linear combination of simpler functions, right? But these simpler functions, of course, can be parameterized in a way that is very nasty, right? So like the canonical way to think about this is to have like these functions that have some input weights W, some biases B, and some output weights A. And then the question is basically we have three axes, right, of complexity, like how many data points do you see, how many dimensions do you have, and then how many neurons are you going to use, like L, D, and N. So in this work, we are going to, as I said, try to gain some understanding of what's going on by taking limits, right? And so the limits here, they're going to come in the order. So first, we are going to think about what happens when the number of data points is very large, like we take the number of data points to infinity, and then we're also going to take the number of neurons to infinity. And we are going to see that in that regime, we can develop we can by scaling things appropriately, we can try to express what's happening, like the dynamics of learning, in terms of if a very, let's say, natural PDE that here, that might be like another connection with physicists in the room, because it's a PDE that is kind of very natural. And then, and actually, what we're going to do is we're going to build on top of this PDE to try to modify these dynamics based on this notion of unbalanced transport that are going to describe, well, we're going to describe what this is about. And this, the whole point is that by this modification, we can improve the convergence properties of this PDE, right? So, that's what I'll try to present today. Okay, so the first observation is that this single hidden layer architecture that I described has a very natural and very kind of clean set of symmetries, right? So if I have a function f that I write as a sum of simpler functions, the parameters θ1 to θn, they are. I mean, any permutation I do on these parameters, it does not change anything about my problem. So then it suggests that a very natural way to think about this function, about this model, is that every parameter θ1 is θ1, θ2, θ3. It's like a particle, right? And then what I have in front of me is a system of n particles, right? And I don't matter which is particle 1, 2, 3. And so in that context, we can just rewrite things. We can rewrite things in terms of these parameters θ1 to θn, and the function, the loss that we have to minimize, in the case where we are just doing regression, can be written as a particular set of basically this corresponds to the energy of a Hamiltonian of a particular particle interaction system, where we can now identify some of the terms that correspond to basically the linear part of this function to some force, right? This sum of f's, and then some term that, of course, captures the interaction between the particles. Okay, so this is the kind of expression we have when we just develop the square loss here, right? So now the question is that let's try to understand the dynamics of systems of particles that follow this kind of Hamiltonian, right? These dynamics. So of course here I wrote down suggestively wrote down the function by doing some kind of linear combination of functions. But if we are going to take the limit when the number of particles go to infinity, there's a very natural first question is, okay, how can we, how do we need to scale the model so that this limit makes sense, right? So this, in particular, this normalization that I wrote here, alpha, how should we choose it? And so this is where the thing gets kind of interesting, because if you look at through the literature, there's not a single choice, right? There are many different choices that you can do. So in particular, one first thing to realize, and you can do it in the back of your envelope, is that because we're going to follow the gradient descent is not scaling variant, right? So basically, for someone who's just working on approximation theory, this is just a constant, right? I mean, if I change alpha, I mean, the function does not really change. But I will be doing gradient descent on this function, right? So this is really changing things around. So if I, for example, if I don't normalize and I just choose as a constant, right? One can actually show, I mean, there's recent papers that show it, that in fact the model, like training these models in that regime, essentially amounts to doing kernel learning, right? And where the kernel is just completely determined by how I sample, how I draw my initial distribution of first, right? And in fact, we can also do a little bit better by, instead of basically normalizing things with a constant, normalizing things such that basically variance, like the variance of the system, is preserved, right? It doesn't blow up with n. And in that case, we still basically operate in a kernel regime, but now the kernel, instead of being the kind of the naive random feature kernel, is a different kernel that was recently introduced by Jacot et al. From EPFL, and something that's called like the neural tangent kernel, right? So basically, think about this as essentially in that regime, my nonlinear function approximation can be understood and can be studied as if it was like a linear. Basically, I'm linearizing the set of the nonlinear function space, and I just learn as if it was a linear system, a linear functional space. But in fact, this is not by all means the only way where one can scale things, right? So if you scale things as 1 over n, you basically you really recover that your function now is an average of simple functions, and now it's much more natural to take the limit to think about a representation that basically writes f as an integral representation against some measure, right? And now this is a general measure, like a general like a Redon measure, and in that case, the right functional space to think about this problem is actually it's not at all. It doesn't have the nice Hilbert structure that you get with kernels. It has a kind of a more, let's say, sophisticated structure that involves some form of sparsity, right? In the case of measures, it's called like the variation norm, right? And this is actually this kind of fundamental difference was very nice, studied in a very, very nice paper by Francis Back a few years ago, right? And so, in a sense, one can see that if you decide to use like the kernel regime, you are essentially using ideas from approximation theory and basically learning that essentially look like linear approximation, right? Basically, you are just working on a on a Hilbert space and trying to find good approximations in a Hilbert space, right? So, whereas in that other regime, what we see is that we have a completely different properties, completely different behavior. And so, in that case, if you just get rid of the learning rate and just think about continuous time, so you just look at the velocity that every particle sees. If you write the energy in terms of this empirical measure, now you can again, I mean, just by substituting the thing, you can write the energy that you have, the loss that you had in terms of parameters. Now you can write it as a loss in terms of the measure. And now what we see is that this loss, right, it's a convex problem. It's a quadratic functional on this measure. So if you look at the velocity, like the particle gradient, like if you use your algorithm and you do gradient descent on the particles, on the parameters, what you see is that if you rescale these gradients by appropriately by factor n, what you can see is that you can actually interpret these particle gradients as basically a velocity field that every particle is filling, right? Basically, it's like now you go from basically every particle is just sitting at one point of the space. Now you're going to basically you have a model where now a density, basically like the probability of finding a particle in a given location, is going to evolve following a velocity field that corresponds to basically to this the gradient, the functional gradient of the energy. And this kind of analogy, this kind of analysis, where now we can think about gradient descent as a form of like a continuity equation, is something that was actually introduced by several papers at the same time, actually, last year, mostly like people like groups from Andrea Montanari in Stanford, Eric and Grant here at the NYU. So once we have this model, what it turns out is that now, instead of thinking about the evolution, like the dynamics in terms of every particle is moving, now we can just think it as a measure that is evolving, right? And the right kind of physical model for how a measure is evolving under a velocity field is known as the continuity equation, and this is the PD, right? So it's a PD that you have to understand in the weak sense. So actually, there's another interesting way to interpret this PD, is that one can interpret this PD as basically doing a gradient flow, but in a completely different metric, in a more general metric space, right? And so the right way to think about this evolution is that basically I'm following a measure that is following basically the steepest descent of the energy functional, but where I measure like the distances. So this analysis, analyzing these PDs in terms of proximal operators, is actually a very beautiful and sophisticated kind of mathematical discipline, and there's many famous papers and many famous probably people that you identify from this citation, right? So it's a very nice kind of a mathematical discipline. Okay, and so what are we building in top of this machinery? So basically, what we are trying to build is trying to understand how to improve the convergent, like to study how can we make the analysis of this, right? So how can we get some understanding and improve the convergent properties of this PD? So what we propose in this work is, instead of just using the continuity equation before, that was just basically particle is going to move according to the gradient. What we are going to do is that we are going to use also, and this extra term in the optimal transport community is also known as the imbalance transport. And so what is the role of this term? So if you look at so this function B, remember energy, the potential energy that every particle sees, right? So what we are doing is that if you have particles that are in the wrong place, right, in the sense that they contribute badly to the loss, we are going to try to remove mass from this place, and we are going to reintroduce them elsewhere, because we are essentially enforcing that the total mass is preserved, right? So think about this idea of you can kind of teletransport mass that is in the wrong place, and you can put it in the good place, and you don't pay the kind of the traditional transport price, like to actually, you can, in a sense, it's for free to move mass from one bad place to a good. Okay, so we are, of course, also discussing, we have in the paper, we also study variants of this equation where we can also introduce a prior measure, but this is not that important. And again, if one takes this proximal interpretation, so we can, again, try to understand this PD. So the right notion of the right metric here, you have to think it as a kind of a hybrid between the Wasserstein that corresponds to the transport and some form of like a Kullback lever that corresponds to this kind of this kind of hybrid metrics were studied in papers by Gabriel and some of his students, Lenny Shiza. Okay, so what can we say about this PD and the convergence properties? So in the case where the kernel is symmetric and positive semi-definite and sufficiently smooth, and we assume that the energy functional is bounded below, in that case we have basically this result that says that the only fixed points of the dynamics are essentially global minimizers of the energy. Okay? So this might sound like a kind of a bit trivial because I just told you that the functional is basically convex. But remember that the convexity here is really, I mean, we are using a completely different geometry, right? I mean, the geometry is non-Euclidean. So in particular, if you didn't have the Grothe terms, what you would see is that this kind of the previous PDE actually in general is not guaranteed to find global minimizers, right? So if you have a convex functional in the space of measures and you just do a continuity equation, you are not guaranteed to find a global solution in general, right? So here we get like sufficient global convergence under mild assumptions, and also we get some kind of like asymptotic. Partly thanks to this new term that we are adding. Okay, so so far we have discussed basically a situation, a regime where we are using a number of particles that is infinite and the number of training examples that is infinite, right? So we have studied the problem in a completely idealistic regime. And so the very natural question is, okay, what is the point? I mean, what is the kind of the usefulness of this analysis? Because in reality, in practice, we have a finite number of neurons and a finite number of data points. So in fact, what I mean here is that at the end of the day, what you would like to understand is you have some test error. And so the test error when I have to use L and a number of n, you can basically use this classic way to decompose the error into different terms. And so you can think about this test error as basically a contribution that comes from training error, a contribution that comes from error, the fact that I don't have the whole data distribution. Also some form of an approximation. In general, I cannot find any function in that. I cannot realize any function in that space. I can only use a finite number of neurons. And so what we study essentially is we have a way to actually control the fluctuations of the dynamics when you are using a finite number of particles, as opposed to using basically the mean field formulation, right? So the fluctuations using a standard like a large deviation techniques are of the order of 1 over square root of n, but only when basically the temporal interval is finite, right? So trying to understand the fluctuations at infinite time horizons is one of the important open questions that we are. So the other important point is this basically the error, and so one of the representation is that it's a very natural way to get like approximation bounds is using Monte Carlo bounds, right? Basically, Monte Carlo bounds are giving us ways to actually understand this thing. But of course, one of the major questions that are still like open is how can we control this estimation error, right? Error, in a sense, depends on the complicated notion of complexity in the class, and so because we are in general not in a Hilbert space, this is a much more complicated term to control. So I just wanted to give you like like some numerical experiments of how this algorithm and what happens in practice. So this is a problem where the target function f of f star Gaussians. So think about this. Basically, I plant a number of Gaussians in different like centers with a fixed covariance, and now you are just basically trying to approximate this function. with a model that is able to place Gaussians at different locations, right? So you basically learn over the centers of the Gaussians and the mixture coefficients. So if you use a standard gradient descent, you get like so if you use the like the unbalanced transport, as you can see, the convergence is faster. And if you use the variant that I described, where you are allowed to actually to create particles from a different distribution that is not the one that you are currently using, like a base measure, you're also able to improve the convergence. And then also we ran some experiments, simple experiments on this framework that actually very popularized by Lenka and other people, like this teacher-student framework, where the idea here is that you can create your own basically training set by having a teacher network that has some parameters, like you generate parameters using a ReLU network, and then you try to recover the same function by trying to learn the parameters of the network. So we have basically a teacher with 10 neurons that we try to recover with a student that has 50. In that case, you can also, we also show through the experiments that what you see, the phenomenon is the same flavor. So adding this kind of birth-death term generally increases improves the performance. And one thing I have to mention is that the way these dynamics are implemented comes at basically zero cost, right? So there's no increase in complexity by to introduce this term. So
What are the spikes?
Yeah, the spikes are related to probably we have a system that basically introduces a little bit more noise, right? Because we are continuously removing bad neurons and adding new ones, right? So if we had a new neuron in the wrong position, it might, at some point produce a spike. But you can see that in general, we have a system that is consistent, right? So basically, eventually, it gets to the global. That's a good question. No, it's a discrete. It's Okay, so I have 2 minutes, so I thought that maybe I would just describe a little bit in detail some of the open questions, like some of the questions that we currently were thinking about, and we are, in a sense, a bit struggling to actually formulate well and to answer. So the first one is what I described, like this analogy, this way to actually map a neural network to a measure is particularly well tailored in the case where you have a single hidden layer, right? Because the symmetries of the neural network are exactly encoded in the symmetries of the measure of the point. How to do the same thing in a deep architecture in a way that it's meaningful, right? So this is something that we are currently struggling. So we don't really, maybe it might be connected with some of the topics of yesterday of like how to actually push this notion of symmetry, right? So if you have now an object that has complicated symmetries, how to encode it, how to actually use these limits beyond supervised learning. So this is something that I think it's also interesting. Then another thing that is currently open is how can actually formalize this large deviation principle? This idea that if I have a good way to describe the behavior at the infinite number of particles and an infinite number of data points, how can I actually formalize what will happen when I have a finite number of neurons, right? So right now, we are using basically ideas from like central limit theorem, but it would be like an interesting question to actually sharpen this analysis a bit more. Other things that are completely currently out of the scope is what happens if we start to use gradient descent strategies that are a bit fancy, like for example adaptive learning rates, right? So this is something that we don't know what. Then another I think like related question that I think is actually quite interesting, more from basically the approximation theory framework, is that we have seen that already with a single hidden layer, there's different approximation spaces, right? There's depending on how you actually normalize the model, you can be in a Hilbert space or you can be in any property of Hilbert space. So in the case where you start actually changing the architecture, making it even deeper, what is the corresponding benefit of the corresponding functional space? And is there like an easy way to think about what is the benefit of depth? Perhaps making a link with the notion of sparsity that Stefan was describing yesterday, that maybe there's a class of functions that maybe come from like sparse inference, where these things are actually naturally not very well approximated in high dimensions with a shallow architecture. So this is something I'm currently particularly interested on. So with that, I'll thank you very much. And this is a reference if you're interested. Okay, it's a good question. It sounds a bit related, but it's very different in the sense that in dropout, you mask a particle, right, for momentarily, but then it kind of resuscitates, drives exactly the same location as it was. Here, when we actually, the other thing in dropout is that the way you actually kill particles, mass particles, is completely independent of their performance, right? So you have basically a Bernoulli distribution variable that is IID that kills particles in a completely indiscriminate. Here we are basically doing a targeted assassination. Right? Basically, we look at the particles that are doing bad, and these are the ones that are going to be killed with priority. But then once we kill them, we forget about their position, right? We create new ones in a completely different location. But you're right that somehow this idea that we are doing, we are basically removing and adding neurons is of course reminiscent.
This like balancing to something about regularization, I guess related to Lanka's question. Can I interpret it as you're adding regularity somehow? Or actually you're not because balancing.
Yes,
Dropout is adding regularity, but you also
so I think that this is, I mean, regularity in the sense of that you're artificially removing capacity, right? You're making it harder for the model to feed the data. But I don't see it like that. I see it more as if you identify one of the weaknesses of this kind of gradient flow, is that it can get stuck in points that it's not the global solution, right? So there are points in which basically you can see that if the gradient of the energy, so basically if you look at the stationary points of the dynamics, they do not completely align with the global optimum of the function. At some points you might be stuck, but it needs a little bit of wiggling in order to get basically you are adding a little bit of noise in the dynamics in a sense. You basically.
I mean, if you relate to Natty's talk yesterday, he proved something about gradient descent is related to some weight, like norm minimization. Yeah. Do you see a connection there? What's your
Yeah, so here the connection is this proximal interpretation, right? When we change the dynamics, right? So if you look at so if you think about the standard gradient flow, you can think that you have like a population of particles that evolve trying to basically minimize the loss while not moving too much, right? This is kind of the moving too much in the sense of fastest time. So when you change the learning algorithm, what you're doing is instead of doing the steepest descent with respect to this metric, you are doing a kind of a steepest descent with respect to a different metric.
It's kind of regularization. Can you interpret?
You can think about this as some regularization, or you are basically deciding that So basically, this is a choice that you are making, right? Your learning algorithm, your optimization algorithm. So how this choice is going to affect generalization? This is kind of the $1 million question, right? It's still like there's still a lot of things we don't know.
Teacher, network. Does it work for more than one layer, or?
I mean, our framework right now is one single hidden layer. It's a good. Yeah. So it's ongoing work. So I will tell you in 3 weeks. No, in 3 weeks. Well, no, in 3 weeks and 1 day. 3 weeks in 1 day. Yes, the NeurIPS deadline.
The question, so if I understood correctly, the density, so the number, the fraction of active particle is fixed in average.
Yes.
But you could also try, I don't know if it's interesting to, so it's like having a chemical potential. So you could actually play dynamically and see, for example, whether at the beginning it's good to have a lot. And then after a certain time, then you increase So it's just increasing the alpha, I think it was. I mean, it's increasing the or decreasing the chemical potential in such a way that you decrease the density of particle.
I see. Yeah, so it's a good point. I mean, we one of the kind of the features by design of these dynamics is the fact that the population is controlled just because of the numeric. I mean, it's impractical to have a model that where the number of neurons basically in the code is basically varying. But I think that maybe in terms of like regularization, having some kind of limiting the number of active neurons could be an interesting
Toward the end, yeah.
or like a sparsity in the charges.
You could also change the name.
Yes.
Back term, you could.
Yeah, exactly. So that's another very important question, right? So if you think about combining two different metrics, right? And so playing with the weights in which these two metrics appear as it's one of the interesting questions that we are studying.